Okay, so it's a pleasure to have Margherita Putti as our first speaker. Thank you all for joining 1 hour early in Europe, because we went to summertime a bit early here. And Margherita will tell us today about gravitational Axiverse spectroscopy, seeing the first for the axions. Please take it away.
Okay, well, first of all, thanks to the organizers for inviting me to give this talk. I'm going to be talking about some work I did with Emanuela Di Mastrogiovanni, Matteo Fasiello, Jacob Litum, and Alexander Westphal. And I'm going to be talking today about, I'm going to be talking today about axions. Well, axions are a solution, have been introduced as solutions to the strong CP problem, and they are everyone's favorite particles because they are, well, very theoretically founded, and there are many experiments that are actively searching for them. But for us, why they're interesting is because they're generic predictions of string theory compactifications, and they make up what is known as the so-called Axiverse. So they're kind of the best avenue in which to test string theory. So I'm going to be talking today about axions in the context of inflation. And why is that? Because, well, inflation is based on slow roll physics, and therefore the very flat potentials of inflation kind of can be subject to ultraviolet corrections. And so in a way, are a natural background in which we can expect to have to see some signals of string theory. And the signatures I'm going to be talking today about are going to be the curvature power spectra and the gravitational waves. All right, so I'm not going to be talking about any specific inflationary model. I'm not going to be interested in the specifics of the inflationary mechanism. Instead, I'm going to be focusing on the fact that whenever you have an axion which is coupled to a gauge field, to a hidden gauge field during inflation, and is not active in the inflationary mechanism itself, it's just a spectator, then it can contribute to the production of gravitational waves and curvature perturbations. So this is kind of the idea of having gravitational waves from the Axiverse. All right, so how do we detect the axions? So whenever an axion coupled to the standard model, we can probe two different types of coupling, the axion photon coupling and the axion nucleon coupling. And here on this picture here, you can see on the left is basically the constraints and the future projections of the axion photon coupling experiments. And you can see that there are really a lot of experiments that probe the axion photon coupling and as well as the axion nucleon coupling, but I'm just going to be focusing here on this. And I don't really want you to go and look at the various experiments that are there. I just wanted to show you that there are really a lot of experiments that are searching for them. And for example, the yellow band is the QCD line, but in general, these experiments are probing a lot of parameter space for the axions. However, they rely on key assumptions that the axion is very light or that it makes up dark matter. And the problem for us is that string axions may not be light enough to be detected, may not be dark matter, but they also can not be coupled to the standard model. And so the question that we wanted to address in this work was how can we probe the part of the Axiverse that does not talk to the standard model? So I'm going to be dividing, let's say, the talk in two. So first, there's going to be a cosmological part, and then the UV embedding part. So this is the cosmological part, and to answer these questions that we have, we use these models that were introduced by Peloso and other people. And basically what happens is that during inflation, you have the inflationary mechanism itself, which is inflating the universe, doing its own thing. And then at the same time, you have a spectator sector, which is made up of an axion, chi, and then the gauge field. And then you have a Chern-Simons coupling between the axion and the gauge field. And it's very easy to understand that whenever the axion is moving, then chi dot is different than zero. And then basically what happens is that in the equation of motion, this term is active. And therefore, you have production of gauge quanta. And then this gauge quanta will produce itself curvature perturbations and metric perturbations and turn out to be the gravitational waves. So for non-Abelian spectators, the story is a little bit more complicated. So I'm not going to delve into that, but the spectra will remain flat. But for Abelian spectators, it's very easy to see that if the axion is rolling down its usual cosine potential, what happens is that initially the axion velocity is null, and then at the end it will be null as well because we have flat plateaus in the potential. And then it will start to take up speed while it's rolling down. So basically you have the initial growth in the production of the gauge quanta and therefore of metric perturbations and gravitational waves. And then we will have a maximum production and then it will decay away. And so it's very easy to see that the final signal, which can be either the curvature power spectra or the gravitational wave power spectra, and here the curvature is the solid line, while the gravitational waves are the dashed lines. You can see that it's just made up of the vacuum baseline plus this source term, which will be exactly like a peak structure. So what we did was that we kind of generalized this mechanism in order to have more than one spectators, but to have a multitude of abelian spectators. And what we found was that the final signal will be just the sum of the vacuum contribution and the various sourced signals for each spectator sector. So for example, here you can see, here we have two peaks which correspond to two spectator sectors. So we have two axions coupled to two gauge fields, and therefore will give us two different peaks. So for the curvature part, I'm not going to be talking about it a lot because it's more interesting in the gravitational wave part, but we can use it and we can probe it via spectral distortions if we're at the right scale, or we can use it to bound the gravitational wave total amplitude because the curvature power spectra has some limits that it has to satisfy. But the gravitational wave part is going to be what is more interesting for us, and we see this in a few slides. And the idea is that it kind of creates a forest, in the sense that if we have, for example, 10 peaks, then we have 10 spectators, and we will have, yes, these 10 peaks kind of look like a forest, a gravitational wave forest, and this is why the term gravitational wave forest. So each peak is kind of determined by the parameters of the axion that we are talking about. So for example, the height of the peak will be determined by the Chern-Simons coupling. The mass of the peak, the mass of the axion determines the width of the peak. And then the initial condition that we give to the axion determines the position at which the peak will show up. And so the reason why this is interesting for us is that this is the typical, a generic possible signal that we can have. And you can see that, for example, we have here 6 peaks, and we will have 6 spectators. And these 6 peaks will be at different scales. And it's interesting because when we go in and look at the possible gravitational wave detectors, which are depicted here in different colors, that we expect to be active in the near future, we see that they are all at different wavelengths. And therefore, the idea is that if we have different peaks at different scales, we can kind of correlate the signal to come out from only one model. That is kind of the idea. And for example, here you can see the BBO, which is this red line here. Then we have the nanograv signal, which is this grayscale here. And these lambdas that I put here basically are saying that if we want to see a signal by, for example, BBO, then we need to have a Chern-Simons coupling of 12.4, because the Chern-Simons coupling, as I said, will tell us how big the signal will be, how strong the signal will be. So instead, if we want to see a signal at LISA scales for the LISA detector, then we need a Chern-Simons coupling of at least 16. If we want to explain instead the recently observed nanograv signal, the PTA, we need a Chern-Simons coupling of at least 22. So this is kind of the values that you need to keep in mind as we go on forward. You need to have a Chern-Simons coupling, which is at least of order 10, 20, in order to have a visible signal in the gravitational wave detectors. All right, so this is kind of the cosmological part. And now we want to dive into the string embedding and the theory embedding. So the idea is that we want to ask ourselves 2 questions. So first of all, is this spectator mechanism possible or generic in the string theory universe? And if so, does the landscape allow for observable signals? So for signals that have a Chern-Simons coupling of at least 10 or 20 order magnitude. So our background will be type to be orientifold compactification. So we take our 10-dimensional spacetime, we compactify on orientifolded Calabi-Yau. And the candidates for our axions will be either the C2 or the C4 axions from the intended P-form fields. We take our C2 and our C4 and we expand it in harmonic forms. And then our CAs or raw A's, where A goes from 1 to H1 will be our 2 axions. And then omega and omega tilde are the 2 and the 4 forms on the Calabi-Yau. And then the candidates for the gauge fields will be the 7 brane wrapped onto 4 cycles. So looking a little bit more in the axion candidate, we take our type to be orientifold projection, which is the holomorphic convolution of the Calabi-Yau and the worldsheet parity operator. And we have to split our cohomology into the positive and the negative part. And then correspondingly, our harmonic basis will be split into the odd and the even sector. And here we'll take the even sector to be the Greek indices, while the odd sector is the Latin indices. So the two remaining non-zero intersection numbers will be the even one and the even odd one. And then we have our new complex coordinates, the axiodilaton, and then the G field, the Kähler field, and our two axions, our two candidate axions, for this spectator mechanism will be the CA, which is the two-form axion, which is odd, and then the rho alpha, which is the four-form axion, and it's even. All right. So where does the gauge theory instead come from? So we have the D7 brane, which is wrapping a divisor over a Calabi-Yau, and then the world volume theory that we get is an n=1 gauge theory, which is automatically coupled to the even axion. And indeed, you can see that when you dimensionally reduce your action, you get two terms for the gauge fields, which will be the kinetic term and then the FF dual term, which is the one that gives us the Chern-Simons coupling. And then they all depend on the gauge kinetic function, which is given by this here. So it's W alpha over 2 pi times the Kähler volume plus I rho alpha, and then other stuff we're not really interested in, where W alpha is just the even wrapping number. And so we can really easily see that the imaginary part of the gauge kinetic function, which is here in the FF dual term, corresponds to the even axion. So we already have automatically a Chern-Simons coupling between the even axion and the gauge field. So after we canonically normalize, because then we want a canonically normalized kinetic term, then we find that the Chern-Simons coupling between the even axion and the gauge field will be given by 1 over the VEV of the Kähler volume. All right, so this is one of the possibilities. And then the other possibility is that if we introduce an odd flux, so a field strength which is quantized over a 2-cycle, which is basically the odd part of this field strength is different than 0, what happens is that we are introducing a coupling with even the odd axion, sorry. So what happens is that basically the gauge kinetic function changes in such a way so that in the imaginary part, we have a new term, which is this kappa alpha BC, CB MC. So basically, we are adding into the imaginary part of the gauge kinetic function a term which becomes a coupling, a Chern-Simons coupling with the odd axion. And after we canonically renormalize, then we get the Chern-Simons coupling, which is WG squared K times M. So we can kind of think, okay, then this is perfect because we have the axions, we have our connected axions, which are the even and the odd axions. We have the gauge fields, which come from the 7 brane wrapping divisors. However, we need to be a little bit careful because there is a subtlety that needs to be taken care of. Because there are Stuckelberg terms that arise whenever you have the 7 branes wrapping divisors. So basically what happens is that you have your Calabi-Yau and you have D and D prime divisors that map into each other under the orientifold. And whenever you have the 7 branes that wrap both divisors, the symmetries of the axion can be gauged. So what happens is that basically the normal derivatives in the kinetic terms of the axion get lifted to covariant derivatives, which have this form here. And this is exactly the form of a Stuckelberg term. So what happens is that basically you can think about it like this. You can kind of reshift the gauge field A in such a way as to have a new degree of freedom in your gauge field, which will become a massive degree of freedom, which is exactly the axion. So what happens is that you are losing the axion degree of freedom and gaining a new massive degree of freedom in your gauge field. And so you have two types of Stuckelberg terms that arise. One is the geometric Stuckelberg term, which corresponds to the eating from the gauge field of the axion of the odd axion CA, and this is controlled by this quantity QA, which is just the odd wrapping number, this defined here. And so what happens is that every time you have a D7 brane that is wrapping both divisors, then if your odd cycle is different, it exists, then you have an odd wrapping number, and this odd wrapping number corresponds to the Stuckelberg term, and the axion is in the gauge field is eating the axion. On the other hand, you can also have a flux-induced two-Hilbert mechanism. And this is controlled instead by this quantity here. So it's given by the intersection number times the flux times the odd dropping number. So it's flux-induced in the sense that whenever the flux is equal to 0, you have no flux, then you have no two-Hilbert mechanism. However, if there is some flux, then this means that that the gauge field is hitting the axion. So why is this a problem? So first of all, it's a problem because you are losing candidate axions, in the sense that they are no longer degrees of freedom, axion degrees of freedom, but they become massive degree of freedom of the gauge field. And at the same time, the problem is that if you have a massive gauge field, then the spectator mechanism doesn't work, or at least it doesn't work in the same way we're thinking of, because of course you want to move something which is very massive, and the more mass it has, then the more energy you need to excite it, and you're not going to have huge gravitational waves. So there will be either a huge suppression in the gravitational waves or nothing at all. So how do we get massless gauge fields? We kind of classified 3 possibilities in which we can evade this two-Hilbert mechanism. And the first class 1, will be when the 2 divisors will be in the same homology class. And we get a U1 from a D7 brane wrapping the orientifold divisor. And since the 2 divisors are in the same homology class, we have no odd wrapping number. And therefore, there is no two-Hilbert term, neither for the odd axion, neither for the even axion. So the 2 possible candidates will be both the odd axion and the even axion, and the gauge field is the one coming from the D1 brane, from the D7 brane, and we're perfectly fine, and we have our Chern-Simons coupling that we had before, and we're good to go. This is a bit of a, let's say, not very generic class. The second class instead is when you have the 2 divisors are not in the same homology class, and so your odd wrapping number is different than 0, is there. But what you take is you don't only take one D7 brane wrapping the divisor, you take n D7 branes, so your gauge theory will be SU1 cross U1. And what happens is that the U1 here, that is here, will eat the odd axion because there is geometric two-Hilbert active. However, you can take the flux to be equal to 0, so you have no flux two-Hilbert. And the candidate axion, the even axion, can be a candidate axion. So now you need another U1 because this U1 is massive because it ate the CA. And so you need to break the SUN to get some U1. So you need to be a little bit careful here because you can break it with flux, but if you break it with flux, then you run into the risk of having a flux two-Hilbert mechanism. So you need to kind of be careful and play around with specific intersection numbers in order to put them, let's say, to 0 to have no flux two-Hilbert mechanism. And then we have class 3. And class 3 is where the 2 divisors are equal to each other pointwise. And you're basically sitting on top of the orientifold, so you have no wrapping number, so you have no two-Hilbert, and both axions are good candidates for this mechanism. However, since you're sitting on top of the orientifold, then the gauge theories that you can have are either SPN or SON, and as before, you have to break the group to get the U1. So you run into the risk as well of using the flux to break the group and then being careful because otherwise you introduce a flux two-Hilbert mechanism. So I mean, it's not super generic, but there are many ways in which you can actually achieve to have a massless U1 gauge field. Right. So we have our U1 gauge field, we have our axions. Now what we need to do is that we need to check if our theory, if our system allows us to have a Chern-Simons coupling of order 10 or 20 in order for us to be able to see the gravitational waves. Because if it's lower, then I do not see any gravitational waves because they are just too low. So first we need to take into account 3 constraints. So the first one we look at is the perturbative control, where we want the fine structural constant over 2 pi to be smaller than 1, basically is the perturbative control of the gauge theory. And so every time we have a U1, for each U1, basically we have to impose this. Then we want, since we want our axions to be massive, we want to give masses to the axions. So how do we do this? Either with ED1s or ED3s. ED1s for the C2 and ED3s for the C4. And we need to impose the control of higher order corrections in an instanton series. So basically, we're imposing that 2 pi times the 2-cycle volume has to be bigger than some order 1 number for the AD1s. And for the AD3s, kind of the same thing. So 2 pi times the Kähler volume has to be bigger than some order 1 number. Here we choose 2 to be for easiness. All right, so we have our 3 constraints, and now we want basically to see whether the Chern-Simons coupling that we were finding before can be of order 10. So the first one we look at is the even Chern-Simons coupling, and recall that we have found that the Chern-Simons coupling for the even axion is 1 over the Kähler volume. And for this constraint number 3, then this means that our Chern-Simons coupling cannot be much bigger than order 1. Then what this means is that, okay, the signal will be there, and we will have some gravitational waves, but it will be so low that will not be observable. For the odd Chern-Simons coupling instead, the story is much nicer because we have 3 quantities we can play with, because we can play with the wrapping number, we can play with the intersection number, and with the flux. And we can boost the Chern-Simons coupling to be of order 10 over of order 20. However, this is not really for free, because whenever you're introducing a flux, you're also introducing a D3 tadpole. And indeed, the D3 charge that you get will be quadratic in the flux. And you can just think of it is that if you have a flux, which is basically the integral over a 2-cycle of F2 is quantized, then in the D7 brane action, you can just think of having the integral of F2 wedge F2 times the integral over our space-time M4 of C4, and this integral of F2 wedge F2 will give you M squared, and then that will be your D3 brane charge. And so we have this D3 tadpole, and we don't want it to be too large. So we don't really know how to put a bound on this, but we go to the F-theory picture. And in the F-theory picture, we have the tadpole cancellation condition that tells us that the number of D3 branes plus basically the flux has to be equal to the Euler characteristic of the Calabi-Yau fourfold over 24, where now we have the Calabi-Yau fourfold because we're in F-theory. And so basically we are asking that our D3 charge that we are finding has to be smaller than the Calabi-Yau, the Euler characteristic of the Calabi-Yau fourfold over 24. And this time 0.1 is to not saturate the whole tadpole, because we allow also for flux stabilization and other stuff like that. And here in the brackets, you see this is of the order of 10 to the 4, because we don't really have an upper bound on the biggest Euler characteristic, but we can say, okay, what is the biggest Euler characteristic that we know of? And that is of the order of 10 to the 5. And so we kind of we ask for our D3 charge to be smaller than 10 to the 4. Okay, so now we can go and check our parameter space. So basically what we do here is that we impose that this lambda is equal to 22, so that we get to have exactly the PTA amplitude, so the recently observed stochastic background of gravitational waves, and we want to explain it, right? So we say, okay, then on the y-axis, we put the wrapping number, on the x-axis is the fine structure constant, and we say, okay, perfect. Now we put our constraints, so the blue one will be the 81, the red one is the perturbativity, and then the yellow one is the maximum allowed tadpole possible. And then the dashed lines will correspond to the different magnetizations, and then the dotted lines are the different values for the tadpole. And so we see that we have the white region is the allowed parameter space that we have. And we actually see that we have a lot of parameter space available. For example, if we are just sitting here, then we have a tadpole of 25, a magnetization of 1, alpha is 3, and then the wrapping number is 3, which are all perfectly reasonable numbers. So that is to say that let's say this mechanism will not be the most generic thing you can ever find, because you need to take into account also the Stukaber mechanism, and you have to play around a little bit with your Calabi-Yaus. But at the same time, we have a lot of parameter space when we actually go and have this system made up. And this is to have lambda equal 22, which is the biggest one we want, because it was the highest amplitude that we had to have to explain PTA. So if you, for example, just want to be observable by BBO, so you need a Chern-Simons coupling of 10, then the parameter space will be even wider. All right, so just to conclude, let me just recap a little bit. So the idea is that we have the string theory Axiverse predicts a bunch of axions. These axions can be coupled to gauge fields. If they couple to hidden massless gauge fields, then we have a gravitational wave forest from multiple spectators. The nice part about this is that the odd axions actually make the best candidate to have big peaks, and therefore we can kind of think as probing the odd Axiverse. However, we know that the Chern-Simons coupling is actually very constrained by a lot of different problems. From the bottom up, instead, if we want to explain, for example, the observation of the gravitational wave background, the one that was 2 months ago, then what happened is that we need to kind of have a big tadpole, or almost big tadpole, let's say. And this translates into having a large Euler characteristic, so a big Hodge number. And therefore, if we have one big peak, we kind of expect to have a lot of smaller, tiny peaks that we cannot really see right now. But maybe like in 100, 200, 300 years, we could kind of see them. And then, yeah, just to conclude, the future directions that we have is to understand what happens if you have actually massive gauge fields, and what will be the gravitational waves coming from that. And to kind of, the other direction that we want to take is to say all of this story in heterotic compactifications and not type 2B. So this is basically my talk. Thank you.
Thank you for the very nice talk, Margherita. Are there any questions? If not, I maybe have a quick one. So it's about how do these results, you see a lot of axions and you can get some of them a mass. How does this precisely fit in with that Putti conjecture? Is there some kind of similar lesson there with the number of axions you see and the amount of charges you need to reduce, that sort of thing?
You mean the tadpole conjecture? Sorry, I didn't hear the word.
Yeah, so the tadpole conjecture is about the complex structure moduli, which you're not talking about, of course, but I was wondering whether there is some similar kind of lesson that we can learn about axions.
Yeah, I don't. So the thing is that the tadpole conjecture says that we cannot have that flux stabilization basically is fixing all of our complex structure moduli. And if I remember correctly. And I think here it's kind of the story is, let's say, talking about the same stuff, but in kind of a different way, in the sense that we're not really putting a conjecture or putting a bound on the number of axions that we get. Is more about the strength of the coupling that we have, more than the number of axions. Obviously, if you have a lot of axions that are contributing in the same way, then you will add up all the contributions. But actually, the strength is much more, the strength of the Chern-Simons coupling is much more important for the tadpole than the number of axions that you actually have.
Thank you. We have another question here.
I just had a quick question. If you're getting large curvature perturbations in gravitational waves, what about isocurvature perturbations, which are highly constrained?
Yeah, so these models actually have been studied in literature, the isocurvature also, in the cosmological point of view. You can actually, I think you can also play a game of constraining gravitational waves from isocurvature perturbation of these models. But they're all the way in which they have been studied and the way in which we kind of use them is that you keep all of these under control and under the limits of detectability. Also for the isocurvature perturbation. So kind of you have some constraint that you need to take care of, and then you kind of play around with the possibilities inside of that of the parameter space. I don't know if this answers your question.
But you're saying you can get visible, detectable curvature perturbations at the same time, not detectable isocurvature perturbations.
So I'm not saying that we can have visible curvature perturbations in the sense that we're not looking at CMB scales, but later. So you could detect the curvature perturbation in the spectral distortions, for example, if you want. But I don't think you could detect isocurvature perturbations at the same level. But I would have to think about the isocurvature perturbation in the spectral distortions.
Thank you.
Yeah, sorry.
In view of time, let us move on to the next talk. But first, let us all thank Margherita again for a nice talk.